things that would help something dissolve in water. Okay, so when we looked at water and salts, we're looking at similar interactions. Okay, or potentially dissimilar interactions depending on how we look at it. When we looked at salt, it's a combination of positive ions and negative ions. Oh, thank you. And when we looked at water, water was a combination of partially positive ions, or partially positive parts and partially negative parts. Right? By matching up those charges appropriately, we could get things to mix. Okay? If we didn't have those interactions or similar types of charges, we wouldn't be able to get them to mix at all. Okay? So we could look at the similarity in those structures or those partial charges. The other thing we addressed is that when we looked at, say, our block of salt here, what phase does that look like? A solid. And if we dissolved that compound, we would end up with some little blue ones and some big green ones floating around. And this would start to appear more like what phase? Okay, liquid or even a gas. How do we transition from a solid to a gas? We added heat. Okay? So something we could do to improve the solubility of a compound, okay, and in particular of a solid, we could add heat. The more heat we provide, the more likely that solid would dissolve, because we're starting to break apart the things holding it together as a solid. Okay? Is that always going to hold true? Well, for solids, pretty much yes. But what if we change the phase? Could we try and dissolve something else in water? Say like, I don't know, oxygen. What can you tell me about oxygen? If I was going to look at it as a reactant, would I expect to be trying to dissolve oxygen? Let's actually change this up. Let's make it carbon dioxide. Would I expect to dissolve carbon dioxide into water as a solid? Why not? CO2 at normal temperatures is a gas. So I'm really looking at starting with the gas phase of CO2 particles and trying to then put those into the liquid, or put those into the water, which then means the end result is that what happens to the distance between those CO2 particles when I dissolve them? Whoa. What is the distance in the gas phase? Really, really, really big. What happens if I now say you can't be in this whole container, you have to only be where the liquid water is? I get smaller distances. What is the result? What does that phase start to look like if I bring those CO2 molecules closer and closer to each other? Starts to look more like a solid. Officially doesn't go to a solid, okay? But we can call it a liquid squiggly line solid. Okay. What we want to do is take that same thought process we used for the solids. Okay. When we dissolve the solid, we added heat. Why did we add heat? More energy to break apart the solid to make it look more like a liquid or a gas. When we are now taking a gas and trying to dissolve that into the liquid, should we add more heat? Why not? We start with a gas and add heat. What's going to happen to our particles? They're going to spread even further apart. And our whole goal on dissolving it is to put them closer together. How can I get gas particles to be closer together? I can cool it down. So I end up changing the temperature to change the solubility depending on what substance I'm looking at, right? Which is a really important aspect, say for, I don't know, the final exam. Right? So looking at the conditions under which we can force things to dissolve or not dissolve is pretty important. Okay? Because your textbook addressed it and I told you to read about it, you all read it, right? Saturated, unsaturated, supersaturated. I do kind of apologize because I didn't really want to talk about it, but since I told you to read it, I figured I should talk about it. Right? We have to understand something about what it means in our saturation levels. So what does it mean to be unsaturated? I can make you pair share and all that fun stuff. Okay, there we go. Let's see, this half of the class, let's do it in smaller groups. Within groups let's stick with the 6 because that works. So we can do our first 3 tables, our second 2 tables, the last 2 tables, and sure, our first 3 tables over here. I want a definition for unsaturated and supersaturated. You can talk to each other. Let's try and talk to each other first. Let's see if we can't talk to each other. Write down a definition for our unsaturated and supersaturated.
Bonds and therefore not containing the greatest possible number of hydrogen atoms for the number of carbons.
Did anybody else come up with that definition? Google did. Google came up with that definition. Okay, so what Google is saying is that if I look at a carbon structure, if I have triple bonds in it, okay, that would be unsaturated, whereas saturated, which I said was in purple, would be if I went through and looked at that structure and had no triple bonds, but then filled it with hydrogens. I should have listened to you, Tanner. I should have let you look at the internet. Because this is what you probably would have found on the internet. Yeah, next time. We'll see. And what is the issue with that? That is for organic chemistry. Good definition. We could apply it to fats, which is a little bit weird because then that starts to make it sound like biology. Screw biology. Dang it. It's more organic chemistry. Okay. That definition does not apply to solubility. That applies to an entirely different system. Much like there and there mean different things depending on their different contexts. So when we're looking at those words, we have to be a little bit more careful about where our definitions are coming from with those. Okay, did anybody come up with a definition for unsaturated? This is one of the reasons why I would have recommended you read the textbook. Just checking. Unsaturated, what do we get on the left? What do you got?
Solution that can accept more of the compound that is being dissolved.
Okay. That can have more compound being dissolved. That's all perfectly legible, right? Close enough? Okay. Supersaturated, what do we get? Anybody? Supersaturated was our right side, wasn't it? Yeah, go ahead.
Bless you.
That has too much. And now I'm going to get irritated because you guys are using some non-science terms. I have to write a whole lot more. Compound that is being dissolved. Okay, it just had to catch up with me. Okay, what is saturated? Okay, I think I actually heard somebody say it's our Goldilocks. Is that how you spell Goldilocks?
Almost.
Yeah.
Close enough? Goldilocks?
It's like solid locks. The D and I switch.
Somebody gave me an easier one. It is just right. We have the perfect amount of our solution to the amount of compound being dissolved. How many people are excited about writing the amount of compound being dissolved? Okay, lots of people seem excited about that by the way you're looking at me. So let's come up with a better word or a different word that means that involves a whole lot less letters because we're lazy and it's easier. Well, our solution is what contains everything. So we're basing it off of, if we want to use some kind of Greek context here, some sol for our solution. Okay, but our shin is apparently one conjugation. We need a different conjugation of that. Solvent works for our solution as well. Okay, they can be used interchangeably. So that's not a bad idea for conjugation, but that takes us right back to solution. So solution and solvent are the same thing. I heard the other conjugation. Solute. Okay, and that's because when you add the letters ute to the end of it, that ends up being the receiver of whatever that action was in English language. Right?
So it becomes a noun?
Sure. But solvent is still a noun. Yeah. I was pretty much just making it up. It's the object.
I see where you're going.
Like if you were the receiver of a mentor relationship, you become a mentute. I don't think that's a word. Yeah, I don't think it is either. Okay. But that's our context. Our solute is the thing that is being dissolved. Our solvent is the thing that is doing the dissolving. And what we're referencing is the relationship between those. A supersaturated solution means that there is more solute in solution than it should physically accept. Okay? Kind of like a game of Chubby Bunny that ends probably in death. Okay? You shoved way too many marshmallows in there, that person ends up suffocating and dying. Okay? And that does happen. Okay? We've pushed beyond the saturation limit for the amount of marshmallows within that person's mouth. Okay? That is now a supersaturated person. An unsaturated person would be boring. They didn't put enough marshmallows in to win. Okay? The saturated person put enough into the mouth to beat the unsaturated, but then didn't put in enough to die, so by definition wins by default. Okay? So we're looking at, this is kind of a morbid conversation.
It's my fault I hadn't wanted to.
I don't see how that's possible, though. Like, how do you get enough marshmallows in your mouth to die, but still be able to say Chubby Bunny?
It's because
Oh, good point. You would lose because you can't say Chubby Bunny. I forgot about the rules. Yeah.
It's also because like the way you can die is like the heat from your mouth causes it to like
Liquefy.
liquefy.
Which is beside our point. So let's get back. We've got our different descriptions of our solutions. We can look at the ability for a compound to dissolve. And what we said, remember, is as we increase the temperature, what happens? For our solids, what happens to the amount of compound that I can dissolve when I increase the temperature? It goes up. So if we take a look at the curve shown here, we've got this plot, this line on it, representing sugar. As I increase the temperature, so as I move to the right on my graph, what happens to the amount of compound? It goes up. Okay? So the more heat, the more sugar dissolves. Are all substances producing the same result? Well, what happens if we look at salt? Salt, when we increase the temperature, what happens to the solubility? It stays roughly the same. It goes up a little bit, but not by much. It's a nice flat line. Okay? So if we were trying to interpretate, close enough, our different levels of saturated, I'm going to laugh at you guys in like 5 minutes.
We know what you meant.
Supersaturated, saturated, unsaturated onto our curve. So let's color code just for the sugar. Where is the saturated line for our sugar? Where on that drawing is saturated? Where is the perfect amount of sugar dissolved for a given temperature? If I'm at 20 degrees Celsius, what is the perfect amount of sugar that I can dissolve? 200, what are our units? Grams of sugar per 100 milliliters of water. What if I'm at 60 degrees Celsius?
About 280.
It's 280, sure, grams per milliliter. Where's our saturated part of this drawing? It is the line. That is our saturation limit. Where are we unsaturated? When we're below that line. Where are we supersaturated?
Above the line.
Above that line. We can use this curve to show or potentially get things to crystallize. And we can do that in, say, organic chemistry, or we could do it in, say, general chemistry. Remember that sodium acetate lab last week? We did try to take the sodium acetate and dissolve that in a little bit of water. Okay. For Tuesday, you guys at least got to see the demo of it. For Thursday, I made you do it, and it all failed. Okay. But you at least saw, or theoretically saw, what happened. A whole bunch of crystals were supposed to come out. Why? You made a supersaturated solution. We went to incredibly high temperatures, 80 degrees.
Almost went.
That's close enough to incredibly high. Okay. And we could dissolve at 80 degrees 370 grams of our sugar. But then what happened after you heated it up? What were you supposed to do?
Let it cool.
Let it cool. So we now dropped the temperature. Did we change the amount of solid in it?
No.
No. So what happens is that our point now slides over to, I'm not sure I went far enough, didn't quite go far enough, to 20 degrees, room temperature. Okay. At this point, I'm well inside the supersaturated system. Okay, so I've tricked the system into dissolving more than it could physically contain. What did we then do? We added a little bit more. We added just enough that the crystals went, holy crap, this is not supposed to be happening. Screw off, I'm going out of solution. Okay? I'm going to go back to where I want to be, which means the saturation. Well, what happened to all of those crystals? Or all of that material?
They condensed.
That condensed into the crystal, and we see the solution crystallize. Okay? It's looking at how we shift and change on a solubility curve.
Works better if you're able to get it almost down to freezing.
Yeah, you'll get more. Okay. We can go through and look at other graphs. I think your textbook has something like this. Notice that not all compounds get you the same result. But as a general rule, what happens when we increase the temperature? Most everything increases in solubility. There are some compounds that don't, and that comes from secondary effects that if you want to talk to me about, you can talk to me after class. But don't worry about it for the sake of this class. Okay? But we're just dealing with being able to roughly interpret that. Okay? For those of you that read the textbook really carefully, there are questions at the back where you could quantify all of those solubility things. I don't think I asked you to do any of that. Yes?
So why does salt not show on the left graph on the graph A goes up?
Let's take a look at the left graph. Where are we starting? Just under 50, and we're ending just under 50. The scale of that is 0 to 500 versus 0 to 100. It's an issue of the scale. Okay. So now that we have these solutions, okay, theoretically we're going to be sitting somewhere in either the saturated or unsaturated amount for our reactions. Okay, so if we take a look at the reaction shown above, what type of reaction was that? It's a double replacement reaction, right? Which you need to be able to acknowledge and see very, very quickly. If you aren't there yet, go back and practice. Right? We want to be able to quantify how much of our product was made. Okay? How do we quantify the silver bromide? Okay, so I run this reaction. I want to know how much silver bromide was made. How would I quantify? What's my quantification unit? Mass, if we were in a solid. Well, is silver bromide a solid?
Yes.
How do I know it's a solid?
It says so in the formula.
It says so with that subscript S. So cool, I can determine the mass of silver bromide. Where did that silver bromide come from?
Silver nitroxide.
Came from the chemical reaction of silver nitrate and aluminum bromide. Okay. So I could go through and quantify how much silver I started with and use that to interpret how much silver bromide I end with. How do I quantify the silver nitrate that I started with? Well, how do we quantify the silver bromide? Mass. So why don't we quantify the mass of silver nitrate we start with? It's a solution. What is the issue with it being a solution? If I take the mass, am I getting the mass of silver nitrate? No, I'm getting the mass of silver nitrate and water. So I cannot obtain the mass of a solution to give me information about the amount of our reactant in there. Okay. Water is now an extra ingredient within that. I would have to somehow subtract away the water from that mass. Okay. Mathematically, that's not easy to deal with. So what do we do as chemists or scientists? Okay, we could try and boil all the water off. Okay, that's fine. So now we have all the water gone, but now I don't have a solution. Can I run the reaction? No. Okay, so I can quantify it by removing all the water, then adding all the water back, and then allowing the reaction to occur, and then remove. That's a bit tedious. What's that? No, we can't quite just ignore it. Okay, what did we do when we tried to compare different substances? I want to compare carbon to lead. Give me a comparison between carbon and lead. Any information you want.
Metal and non-metal.
Metal and non-metal. Quantify it now. You gave me a qualitative observation. I want a quantified observation.
Atomic mass.
Atomic mass. Okay, what is the atomic mass of carbon? 12. And the atomic mass of lead?
207.2.
207.2. Okay. I can quantify looking at that mass. Okay. What are the units on that 12? AMUs or grams. Okay. Where did I come up with grams or AMUs? Couldn't it have been pounds? Why did I use grams?
Because it's always in metric.
We stick with metric. Where did the metric unit come from?
You memorized it.
What's that? Some guy put a kilogram block on a scale and said, this is a kilogram. Where did our unit come from? That guy. Okay. We didn't have a way to do a comparison, so what did we say? We said, it is defined as this. We invented a unit. What are we going to do here? We're going to invent a new unit. That new unit is molarity. Right? This is shown as capital M, okay, which we've seen in the lab pop up a couple different times. Sorry, Skittle Farts is not a real conversion unit. Okay, though you can try when you become fancy enough. See if you can't get that adapted. Okay. Just don't tie my name to it. Okay. Molarity, or capital M. I would argue the unit of capital M is not useful. Because that's too confusing of a unit. It's really a combination of units. That combination of units is the moles of the substance per the liter of the solution. So now if I looked at silver nitrate, and I wanted to know something about how much silver nitrate was there, if I said I had 3 molar silver nitrate, does that allow me to be able to quantify how much silver nitrate was there? Well, that's really just saying I have 3 moles of silver nitrate per 1 liter. Okay. How could I use that to quantify the moles? What other information would I need?
Stoichiometry.
I'll kind of accept stoichiometry, yeah?
Avogadro's number.
No, not Avogadro's number. Grams, so there's an interesting idea. If I brought in grams, well, that just convolutes the unit. I'd have grams times moles per liter. Okay? But I like where you're going, trying to get grams, a measurement. Okay? Could I potentially do a conversion where I get rid of, say, the moles? Okay? That conversion factor I can find where? Periodic table. Man, I can't spell, I can't write. PT. Let's just leave it at that. Okay. But I still want to quantify. This is now a grams per volume. I want to know exactly how much is there. What other information would I need? No, the molar mass is our periodic table. That's our grams and moles. What unit needs to disappear to give me an exact mass amount? Liters. What other information do I need? How about the volume of that solution? Can I measure the volume?
Yes.
Yes. So I can end up using the molarity as a conversion factor that allows me to get a mass quantity from a volume quantity. That's pretty useful. Okay? So we're going to be using molarity just like we've used every other conversion factor. We'll set it up, we'll process it into our conversions to try and work through it. Okay? So what is the molarity of a solution containing 24.0 grams of what compound? Sodium hydroxide in 0.1000 liters of solution. Right, like we would do every question, where do we want to start? Where I want to end. What am I trying to solve for? Molarity. And we could go through and write that as the big capital M, and I would again argue that's a bad idea. We should write it instead as a unit that makes sense, which is moles over liters. Okay. Next step. Write the what? What I'm given. Okay. I'm given two pieces of information. I'm given 24.0 grams and 0.100 liters. Which one do you want to work with? Okay, liters. Okay. Where do I want to put that liter system? Where do I want to put this value?
Denominator.
Why do I want it in the denominator?
Because that's where it is in the answer that you want to get to.
If I look at my answer, liters needs to show up in the denominator. I'm going to have 0.11 liters. What should show up in the numerator? Is it telling me 24 grams in 0.100 liters?
Yes.
It's showing me a calculation of how to make that. Is the information given 0.100 liters and 24 grams?
Yes.
They're two separate topics.
It says
Okay.
contain.
If we mash them together, we are combining two calculations, and I would argue you should not combine your calculations. Are you going to be wrong in this case? Mathematically, no, but it's coming down to condensing steps versus not. These are two separate things. What should show up on top would be just one. Okay? Yes, Simon. The textbook, I also told you to completely ignore chapter 17 because it was really, really freaking confusing. How many people, because you had the textbook, went through and did all of the calculations in chapter 17? You did not do all the questions in chapter 17. Put your hand back down. The textbook does some things nicely. It does other things confusingly. I would argue that you should try and keep your calculations as separate as possible. If you want to combine calculations, combine them correctly, I have no argument. Combine them incorrectly, all you're going to get out of me is okay. Follow what I asked you to do and we don't run into that issue. Okay. This gets us liters in the denominator. I don't have moles in the numerator yet. So ideally, what do I want to have happen in that next step? I want moles. Am I given moles? No. So now we run into a crossroads. What should we do? Do we want to work with some kind of conversion factor here, or should we change that moles to the 24.0 grams? Both answers work. What do you want to do? Change it to grams. Okay. So we're going to say we need to bring in our 24.0 grams. And what would show up in the denominator? 1. Okay. We should be showing our full units. It should be grams of sodium hydroxide. So if I did this calculation, what would I have as an answer? Don't tell me the number, I want the units. Grams per liter. What answer do I want? Moles per liter. What does that mean I need to do? And in that conversion factor, what do I know needs to happen? And ideally, what do I have on top? The moles of sodium hydroxide. Where do I find the conversion factor between the grams and moles? The periodic table. And I would do that, because we've had questions on this before, by looking up the molar mass of sodium, which is molar mass of oxygen, hydrogen. I would add that all up. Somebody gave me a number, I think I heard. 30? That was 40. It's just 40. 40 grams in 1 mole. What happens to our units? And we would end up with moles over liters. We now have our answer in molarity. Okay. It's setting up our conversions, plugging in the units that we need, and working our way through it. Questions? Okay. Okay, step 1. Define what you want for an answer. We want grams of potassium dichromate at the end. The next part becomes tricky because, again, we're given 2 pieces of information. We're given the molarity and we're given the volume. Okay. Neither of those give us units that we want. The final unit we want is grams. Okay. So maybe what we should do is step 1 is say, well, what the heck is capital M? Which means what? 0.150 moles in 1 liter. Okay, that's what that means. So you should immediately be writing that down, getting rid of that capital M. Okay, we have milliliters, we have liters, we have moles, none of which equal grams. Okay, so figuring out where to start now may be a bit of a challenge. Okay, so let's think back to all of the conversion factors we've looked at. Is there a conversion factor that I'm aware of somewhere back there that allows me to convert 2 grams from either moles or liters or milliliters? Okay, I'm hearing milliliters to liters. That is a valid conversion. Okay, but which way should you include it to get grams? So what you'd be doing is a secondary calculation in 2 steps. So what I would argue is we should hold off on the milliliter liters and figure out first how we can get grams. What conversion factor allows me to convert between grams and either liters or grams and milliliters or grams and moles? Grams and moles. Where do we find that? Periodic table. Okay, so I do have a conversion factor that gets me grams. Okay, where do I want that gram unit to show up? On the top. Okay, where do I find the numerical values to go into that? The periodic table, which is an irritating calculation to add up, and I sort of apologize for that, but you needed the practice anyway. We go out to our periodic table, we figure out the mass of potassium times 2, the mass of chromium times 2, the mass of oxygen times 7, and we would end up with 294 is close enough for my taste, grams per mole. 294 goes in, 1 mole goes there. So cool, if we now look at what I've set up here, grams is in the numerator, and what do I want for an answer? Grams in the numerator. It's perfect. It's exactly where I want it to be, except I've also brought in moles. Do I want moles? No. So I need to get rid of that mole unit. That means I have to now do another conversion, or have to do a conversion. And in that conversion, what do I know needs to show up? I need moles on top. Okay, am I given moles explicitly in the question? No. What am I given explicitly in the question? The molarity, which is the moles per liter, which means this is not just moles, this is moles over liters. Okay? What numbers need to go into this? 0.150 goes on top. Why does it go on top? It's with the mole unit. What goes up on or goes on the bottom? 1 liter. what happens with our units? The moles cancel, and I now have grams per liter. I still have my grams, that's good, but I have liters still. Do I want liters? No. So ideally what I would then have to do is another calculation. And in that calculation, ideally I would put in liters. Am I given liters? No. Okay. What am I given? Milliliters. So I could do a conversion between liters and milliliters. How do I do that conversion? Okay. Okay. Thank you, Naya. Back to how I told you to do this. You need to memorize what your prefix means. The prefix milli means 10 to the minus 3 goes in front of our base unit and 1. If you don't want to memorize it that way and you want to deal with 1,000, you can. Just realize there's a high likelihood you'll screw up kilo. Okay. What unit do I now have? Grams per milliliter. That's not what I want, so ideally I need to do another calculation here where I have just the milliliters. Am I given just the milliliters? Yes. Over what? 1. Now I can punch it into the calculator and I have my answer. And whatever that number is. What'd you get? 5.52 grams potassium dichromate, assuming Simon did the calculation right. Can I get a second on that? 5.51 is close enough for my taste. Do we have the proper number of sig figs? Yes, because of our molarity being only 3 sig figs. Okay. So this is a fun little game that we're now going to move into. What just happened? Oh, I know what happened. Sorry. We're now going to apply molarity to everything we've looked at. A chemist needs to determine the concentration of a solution of nitric acid. She puts 745 milliliters of the acid in a flask with an indicator. She then slowly adds 0.200 molar of barium hydroxide to the flask until the solution changes color, indicating the equivalence point. Okay, so the equivalence point is when the moles of nitric acid is the same as the moles of barium hydroxide. It's kind of an important little definition there. She notes that 165 milliliters of barium hydroxide was needed to reach this point. What is the molarity of the nitric acid? Okay. Beginning to end, this is something you are responsible for. It is what you will be doing in lab in a couple weeks, I think. Okay. So we need to be able to think about and approach this in combining everything that we've learned so far this semester into one giant cluster of a problem. So to that end, because I want you to work seriously on this, I want you to do teams of 4. And what I will do within those teams of 4, I'll even accept 5, I will pass out a piece of paper and I want your names on that piece of paper. Okay? And to increase the likelihood you'll do this, I will give you 5 points extra to exam 3. Okay? For your ability to do this. Okay? What I want you to do is to develop the process to solve this question. I don't want the answer, though if you do the answer, that's fine. Right? But what I want is the process. Right? What you will then do is use that process to solve the question, and you cannot deviate from your process. Right? So everything we've been doing has been going through a process. What I'm asking you to do now is to identify the steps of that process. So some key concepts that you might want to do is summarize the question. What information has been given to you? You then need to analyze parts of that process or that question to figure out what you need to discover. You then need to be able to synthesize all of that information together to come up with and solve the whole question. We good with that? We got 15 minutes to put together your process. By 15 minutes, I'm really only going to give you 10. Wherever there's groups of 4, you need to call them out so that I know. Where's our group of 4? You can do a group of 3 too. I'm fine with that. Yes, you can write pencil. When the name is on each of those sheets of paper or on the sheet of paper, this does not mean writing down your directions and saying take this number times this number. All the individual steps necessary to go into this.